Hello, Mr. Aaron, Mr. Ryan, are you right? Yeah? Okay, so knapsack. Knapsack. We talk about some knapsack problem, yeah? Knapsack. Knapsack actually is like a bag, okay? A bag. So we have a few items, yeah? A few items, like, and each one has weight, right? The weight, let's say we have 3 items, 1 kilo, 2 kilo, 3 kilo. Okay, and then for each item we have values, right? For example, the first one has 1 pound, $1 US dollar, okay, $5 US dollar, $3 US dollar. And this knapsack, yeah, can hold at most what? Capacity 5 kilo, okay? 5 kilo. So for each item, obviously we only have one. You can pick it or not pick it. So what's the maximum value we can pack these items into the knapsack, the bag? Okay, right? So which these 3 items, which one you want to pick? That's so to maximize the value in the bag.
The last one.
This one, and look, we have capacity 5. So if we pick this, we have 2 more. Remaining 2. So which one we should pick?
The middle one.
The middle one, yeah. So look, 2 plus 3 is smaller or equal 5, and the value we get is 5 plus 3 equals 8. So this is the maximum value we can get. Okay, so let's call the 0-1 knapsack problem. 0-1. So let's formalize this a little bit. Okay, so look. Each one we can pick or not pick, right? Which one we can pick or not pick? Let's put it as pick P, okay? P equals 0 value, yeah? 0 or 1 value, okay? So if we pick it, we use the 1. If we don't pick it, it's 0, okay? Alright, so we want to pick the item, we want to maximize what? Pi times I index, yeah. Pi times Vi. We want to maximize this, yeah. So that's the sum of it. So maximize. This is sum, okay. Alright. When this is sum, I from 0 to n minus 1. N is the number of the elements in number of items, yeah. Number of our items. Okay. Sum. Can you read this? Sum. I from 0 to n minus 1, Pi times Vi. When it's 0, what does it mean? We don't pick it. When it's 1, we pick it, right? But this is the maximum. This is our target. We want to maximize this. But we want to suggest to what? It suggests to what? We don't want the total weight except the capacity, right? So total weight is what? I equals 0, n minus 1, weight, yeah? Weight will be Wi times Pi, yeah? Is less or equal than C, okay? You see? Less than equal C. Wi is the weight times Pi. Look, if it's 0, it doesn't use up the space. If it's 1, it uses up space, eh? Yeah? Okay? So, and then also we need to say Pi belongs to 0 and 1, okay? Yeah? This makes it a 0-1 knapsack. Okay? Can we choose the most valuable one? If we go for this strategy, can we choose the most valuable one? Can we choose? Look, what's your strategy here? What you pick the? Why you pick the last one at the beginning, not the middle one?
It's because. I don't know.
Because these are 3, yeah, you just randomly pick one, right? Okay, so it might not work, right? Why is that? Because look, if this is the most valuable, how about it's very, very heavy, yeah? You can't pick it. You can't obviously put this 100 into the C equals 5, right? So this doesn't work.
That's heavy.
Yeah, that's heavy. I'm
1.
How about there's another strategy if we consider V divided by W, the ratio, yeah? The unit, the most valuable item in a single unit weight. For example, that would be 2.5, that would be 1, that would be 1. And how about let's put it 1.1 here. right? So let's put this, yeah, we pick this 2.5, but the next one we pick 1.1, which is not clearly not the optimum, right? Yeah, because this misleads us to pick this, but obviously we need to pick this one, right? Yeah? Make sense? Yeah? Okay, so for each item we can pick or not pick. So how many items? There are n items. For each one I can pick or not pick. So how many choices do we have? The first one we have two choice. The second one we have two choice. The third one we have another two choice. So what's the time complexity if we brute forcing this? That will be equivalent of finding the subsequence, right? Remember the subsequence. Subsequence. Not continue, yeah? For each one we can pick or not pick. Each one, the first one has two choice. The second one has two choice. The third one has two choice. We have n items, so they are n choice, right? N choice here, n choice. The time complexity is 2 to the power of n, right? This is equivalent of finding the subsequent, the number of subsequent, yeah? Yeah? So yeah, so the time complexity will be this one. Picking the number, and obviously we need to times n to find out the to sum up, yeah, to sum the values up, right? So this is not very feasible, it's practically very slow, okay? But as we said, for each one we can pick or not pick, and if we can write it, right? If we can use the computer to remember it, remember? Yeah. If we said, okay, we ask computer to remember it, what kind of algorithm come to your mind?
Memorization.
Yeah, I know.
Programming.
Yeah, dynamic programming. Okay, and we use the top down today, and tomorrow we'll talk about the bottom up. Okay. Okay, so for each one, yeah. So look, define. Let's define.
Define cache.
Define. Let's say
Depth of search.
depth of search. And then for two parameters, the first parameter I, the second parameter C.
Why is there I and C?
Okay, good question. That's a good question. What does it mean? It means that we are. Remember the numbers we're picking, yeah? Yeah, we're picking the numbers. Remember? Yeah, it's quite similar to that problem. We are picking the ith item. Okay, we are picking the ith item. Okay. Yeah, the first item is 0. Yeah, we are picking with the ith item, and then we have capacity C in the knapsack. Okay, look, if I equal length, the weight or value, yeah, doesn't matter. If we are running out of items, so we return the value, which will be what?
Return
0, right? Because look, we are running out of item, which if I is the last.
Why do you need to write rates? Why couldn't it be values?
So, yeah, it's the same. You can put a value. Yeah, it's the same. It's the length, right? The length of the values and weights are the same. Yeah, different. The same thing. Yeah, represent the number of items. Yeah. Now I can get the answer at the beginning of 0. Okay. Now if this capacity, we have capacity equal bigger than equal the weight. Current item is weight I, right? So look, we have capacity C, and the current item has weight, this weight, right? If we have enough capacity to pick this item, right? So we can pick it, we can try to pick it, right? We can try to pick it, answer equals max answer. And then if we pick it, DFS, we need to pick the next item. And what happened to the capacity? If we pick it, what's the capacity left?
C
Minus weight I, yeah, we just need to minus, yeah. I, yeah, this one. And then we have picked this, so we gain the value, right? Plus value is what? I. Make sense? Right? And obviously we can choose not to pick this item, right? So I can say answer equals max answer. We're not picking it, DFS, but we try to move to the next item, yeah? And then we still have capacity C if we not pick it, right? Yeah? Return answer. Make sense? What's missing here? Cache, yeah. If we're not putting this cache, right?
It's exponential.
Exponential, as I said, all to the power of n, right? Yeah, to the power of n. Because each one we can pick or not pick. Each one we can pick or not pick. I and C, right? So it's actually what? I and C. So I will be the item, okay? If we list the values here, okay, this is I. I will be the number of items, yeah? So it will be 0, 1, 2, here, n minus 1, right? This is the item. And then C is the capacity. 0, 1, 2, blah, 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 blah. Yeah? Yeah, we show this table before, yeah? If we want to pick this n minus 1 item, and then capacity C somehow here, yeah? C somehow here. I want to compute this value. But the computer needs to go through this, okay? Then you look for what? For the values here somewhere, and then these would be, again, we need to calculate, in order to calculate this value, I need to calculate a few more values, right? Yeah? But each time I calculate this value, right? I may have to calculate the same pixel, same number again and again, right? Yeah? But if I put a cache, what's the maximum number of values I need to compute in this table?
C times n minus 1.
C times n. Where down C times n? Yeah, yeah. If I put a cache, right? Because every cell I only calculate once. If I calculate it, and what do? We store the numbers in the cache, right? So the next time you just look it up the value, and you don't need to do it again and again, right? Okay. Yeah. Look at this one. Yeah. If the current capacity is bigger than the weight, then we can pick it. We can try to pick it. When we try to pick it, the weight needs to subtract this, but the values needs to plus it, right? Yeah? Right? And look at I 0 to n, and we can start from I backwards, yeah, from n minus 1 to 0. This is the same thing, yeah. This implementation is from 0 to n minus 1, because look, this is plus 1, right? If we start from n minus 1 to 0, this will be minus 1, and then this will be smaller than 0, right? Okay? Yeah? Yeah, smaller than 0. Okay, let's write this. Look, if this is smaller than 0, right? Smaller than 0. And this needs to minus 1 here. And then in order to get this value, we just return DFS n minus 1, which is length of weight or length of values, n minus 1. And then at the beginning, we have capacity C. Right? So it will be start at this value. Yeah? In order to calculate this value, what happened? We might have to calculate this value here if we don't pick anything. Or if we pick that item, could be somewhere here, right? Somewhere here, right? Somewhere here. Right? And again, in order to calculate this value, we need to calculate this value or somewhere here, right? Got it? Yeah, so this looking up, this is top-down dynamic programming if we put a cache. Yeah? Make sense? Anybody? Any questions?
No.
No questions. Okay, are you sure? Okay, can you explain to me what's this? What's this bit? What's this bit? This is the most important thing to take away for the cache. Can somebody explain to me what's this? Why we need to check?
If the capacity is greater than the weight, which is good because wait.
If this is current remaining capacity of the bag, right, the knapsack, is bigger than this item, well, wait, we can try to pick it, yeah?
Yeah, you can put another one.
You can put it, and then once we put it, what will happen? We need to subtract the weight from the capacity, yeah, to the DFS. But again, we get a value, right?
And then you can get another one.
Yeah, and we can get a value. This is just two choice, yeah. This choice is that if we can put a value, then we try putting it, right? Because basically for each item we only have two choices. We pick it or not pick it, right? Okay, right? We pick it. This one is we don't pick it. If we don't pick it, we try the next item. Why this is C? If we don't pick it, this is very obvious. Why this is C?
Because the capacity. Capacity.
Capacity. Why is it still C? If we don't pick it, why is it still C?
Because because you did nothing changed to it. Because
We don't nothing change. Yeah. If we don't pick it, nothing change. We try next item, right?
Yeah.
If we pick it, we can pick it. We try next item, but the weight needs to be subtracted and the value needs to be, yeah, that's the maximum value, and we get the maximum. Yeah. Yeah. Okay. The time complexity O times C times N. Yeah. As we said, right? If we put a cache, it's O C times N. Okay. And if we don't pick it, it's O to the power of N. Yeah, O to the power of N actually, because each one we pick and times the N, right? Times N, okay? The number of items, yeah, we need to pick to the number of items N, and each one we can pick or not pick. So actually this is the same as iterating the array and try each subsequence, right? For each subsequence, we need to compute its weight, right? Its values, right? Yeah, its values.
Oreos.
Yeah. Okay. That's it for today. Good job. Bye bye. Bye bye.